In this session, we will finish up Chapter 2. Remember that Chapters 1, 2, and 3 are really a review of Algebra 1. So we're going through them fairly quickly. This first part, we're going to cover 3 units here. We'll do the absolute value, and then we'll move on to using proofs in solving equations. Then we'll move on to reasoning strategies, and we've looked at a number of these already. Here are the ones that we are going to be using this year. Almost always, because of course we're doing algebra, almost always we'll be writing an equation. We've already looked at this one, drawing a diagram. This is the one we're looking at today. And in Chapter 3, making an organized list. And you can see there are other reasoning strategies that we will use later on. Let's get started. We're going to be simplifying absolute value expressions. We know an expression is different than an equation. An equation always has equal sign. Use absolute value to find the distance between 2 points on a number line. Absolute value will give us a undirected distance without any regard to which way that distance is going. And then we'll solve and graph absolute value sentences. When we get to a sentence, we're starting to talk about equations. Okay, we're going to graph these. It's just a quick review. We see that our boundary is at 0, so we'll put in our boundary point right here. Are we going to fill it in? Yes, because it includes the boundary point. Whenever you see the equals, that's what it is. And we're doing everything greater than that. This one, I don't think I should start looking at the boundary point until I simplify this. Do you agree? We'll add 1 to both sides. That will 0 this and make this a 1. So now that we've got it simplified, we can put in our boundary point, which is at 1, and it is solid. And we're saying everything less than or equal to. How about this one? Well, here's an example of a compound where we're going to have 2 boundary points. One of them is at -2, and it does not include -2. There's no equals there. And the other one is at 2. And we're saying all x in between those, all x that are greater than here and less than here. This is an example of a conjunction. That's where we have an intersection of statements. And this would be an intersection of x is greater than -2 and x is less than 2. This one here, let's see, this one will also be a conjunction, but I can't use it yet. I have to simplify it. So I'm going to subtract, add 2 to each member, and I end up with 1 as a boundary point and 3. And those will be open circles. It does not include the boundary point up to, but not including 1 and 3. So again, we have a conjunction. It is the intersection of x is greater than 1 and x is less than 3. So we spent a little work on the number line just to remind ourselves of our last lesson. Now we're going to talk about the absolute value of x. If x is positive, then the absolute value of x is the same as x. However, here's where it gets more interesting. If x is negative, then the absolute value is the additive opposite of x, making it positive. For example, let's look at 1 here. I have to do my work inside of parentheses first, right? Please excuse my dear Aunt Sally. You do work inside of parentheses first. Now you may be thinking, absolute value, that's not parentheses. Well, anything that brackets an expression together can be considered in the same class as parentheses. So we're going to do this operation before we do anything else. So this is the absolute value of negative 15. And we know when we have a negative number, and we take its absolute value, it becomes the positive version. This one, what are we going to do here? Well, we don't have anything in parentheses, so we're going to take the absolute value of negative 3, which is 3, and we're going to multiply that times the absolute value of positive 5, which is 5. Is negative x always a negative number? Well, suppose x equals negative 2. If that's the case, then a negative x equals negative of negative 2, which becomes positive. So clearly, negative x is not always a negative number, so our answer is no. Does negative, the absolute value of negative 3, equal negative, the positive value of negative 3? Indeed, it does, because what is the value, absolute value of negative 3? That's right, which is the same as this. So we say yes. Does the absolute value of negative 3 equal minus the absolute value of 3? Let's try it. This would be a 3, and this, the absolute value of 3 is 3. You'd end up with something which was not equal. So in this case, no. Let's work with absolute value for a minute. We're going to multiply these two together. And we'll get 3y. Now, is it possible for us to simplify that any further than that? Yes, yeah, we could say the absolute value of 3 times the absolute value of y equals 3 the absolute value of y. Can we simplify that any further? We cannot. That's as far as we can go, because for all we know, y is a negative number. Let's look at this one. Now we can see we could divide this up into the absolute value of a squared times the absolute value of a. And we know that the absolute value of a squared, well, forget absolute for a moment. The value of a squared will always be positive. Is there any way in the world that it could be negative? No. Even if a is negative, you still can't. When you multiply a negative times a negative, you get a positive. So I actually can pull that right out from its absolute value signs, because I know it's always positive. and I do have to leave the a in here just in case a is negative. How about this one? Well, this could be written as the absolute value of a square times the absolute value of a square times the absolute value of b square. If a is negative, or if b is negative, it's never going to go negative. So I can remove the absolute value brackets without any fear of corrupting this. So this could be written as a square times b square. Even if any one of these, a or b, are negative, it's still going to be positive because it's being squared. Of course, I would write it this way. I would simplify it. All right, this next one looks a little more complicated. Let's write it out this way. The absolute value of y divided by the absolute value of z squared. Here again, when we have something squared, there's no potential for us having to change it from negative to positive. It's always going to be positive because it is squared. So I can do this. And this last one. Now this could be written as the absolute value of negative 3 times the absolute value of y. What is the absolute value of negative 3? That's right, it's 3. And the y, we cannot remove the absolute value symbols because it may be that y is negative. Let's try graphing. The absolute value of a minus b. If, let's say, we're talking about this, a, and let's put some numbers on this. Let's say this is 0, and this is negative 2, and our b is a positive 3. Okay, the absolute value of a minus b is the absolute value of negative 2 minus a positive 3, or the absolute value of negative 5. Over here, the absolute value of 3 minus a negative 2 is going to be the same as 3 plus 2, absolute value of 5. And both of these are equal to 5. And we see that right here. 1 unit, 2, 3, 4, 5. These are 5 units apart. So the distance between these two is 5. We're going to graph absolute value here. The absolute value of a equals 2. Well, what are the possibilities? We're going to take a look at all of them. And let's put them on here where they belong. A could be 2, or it could be negative 2. If a is negative 2, the absolute value of this would be equal to 2. If a is a positive 2, the absolute value of positive 2 is going to be 2. In either case, so here we've got 0, and we go 2 in the positive direction and 2 in the negative direction. And those are the two possible values of a. So this was an equation where we're dealing with a point. In this one, we're going to deal with inequalities. So we're going to deal with a range. We have the same situation with a boundary at -2 and a boundary at +2. And it'll be the distance between them. So we have a range of solutions here. Point solutions for an equation, range of solutions for an inequality. This one turned out to be a conjunction. And what do we see down here? A disjunction. I should point this out to you. Whenever we've got the less than, we're talking about a conjunction. When it's greater than, we're talking about a disjunction. We have the same boundary points in all three of these. We've got a -2 and we've got a +2. In this one, we're talking about A being greater than 2 over here, or a -A, which is greater than 2, which translates into A is less than or equal to -2. So let's try these. This is either going to be, let's take the positive version of this first, 2x minus 4 equals 2, or when we take the negative version of this, it's going to be negative 2x minus 4 is equal to 2. So the positive version first. That would give us 2x equals 6, or x equals 3. On my negative version, always when we have absolute value, this expression in here may be a negative or it may be a positive. Okay, so that would become negative 2x plus 4, good for you if you saw that right off, equals 2. Nothing's happening over here. What did I just do? I distributed that negative. So I've got a negative 2x equals, I'm going to subtract 4 from both sides, a -2. I divide both sides by -2, I get x equals 1. So let me write in some numbers. So I've got 1, 2, and 3 that I'm really interested in. I've got this point here, and I've got this point here. And that's what I've got, points. Why do I have points here? Because we're dealing with an equality. What's going to happen with this one? With this one, I'm going to have a range of solutions because it's an inequality, and the same thing is true down here. All right, so I have a positive version of this. 2x minus 4 is less than 2, and I'm going to have a negative version of this, which is going to be just like up here, isn't it? I'm going to have negative 2x plus 4. That's the negative version of this expression here, is going to be less than 2. Now this gets a little more interesting, I think. We're going to subtract 4 from both sides. I get a negative 2x is less than -2. Now I have to divide by a negative. Anytime I divide by or multiply by a negative in an inequality, the symbol changes, doesn't it? So I end up with x is greater than 1. So I've got, now we're going to use the same 0, 1, 2, 3. I've got Oh, I haven't completed this one yet, have I? I'll do it in red. 2x is less than 6, x is less than 3. So I have this point here, which is open, because it doesn't include the 3, and less than. I also have this point, 1, and greater than. So there's my solution right there. It's a range. Now I'll do this one. This will give me, for the positive, 2x minus 5, that's the positive version of this expression, is greater than or equal to 1. I'll solve for x in this inequality, greater than or equal to 3. So if I use the same number scheme, only this time I'm going to fill it in, aren't I? Now I'm going to do the negative version of this, which would be negative 2x plus 5 is greater than or equal to 1. Negative 2x is greater than or equal to, I'm going to subtract 5 from both sides. So I have a negative 4 here, don't I? Now I'm going to divide both sides by negative 2, so my sign, my symbol, is going to change, and I'll have x is less than or equal to 2, right? I divide a negative 2 by, divide a negative 4 by a negative 2, it gives me a positive 2. My boundary point is at 2. Now let's take a look at the, I should put the numbers in just so it's really clear. For this one, I'm saying greater than or equal to 3, so I'm headed in this direction. And for this one, I'm saying x is less than or equal to 2, so I'm headed in this way. This is a disjunction, right? Moving on to section 8, proofs. I love proofs. You may have a little bad taste in your mouth, but we'll try and sweeten that up. Solving these, I'm going to skip right over this. You can stop for a minute and do them if you would like. We're going to move right into conditional statements, which always take this form. If, then, if, then. Occasionally the then isn't mentioned. If I don't study for the test tomorrow, I will fail it. I didn't put the then in, but we know that's implied. This if can be referred to as the hypothesis, and the then is what is going to happen, the conclusion. So the hypothesis and the conclusion here. We can also think of it as the given, what's given, I didn't study, and then the thing that I need to prove that I fail. Another, I think this word shows up in your text. I don't think I'll be using it much, but the antecedent, what does, those of you who take Latin, you could help me out with this, right? Antecedent and the consequent. Whew. No, I definitely won't be using those words much, but you see them in your text, and that's how you think about them. When we are doing a proof, we always start with our given, so let's get going with that. So here's our given. How do I justify putting that into my proof? This is the easiest part of the proof. I just say, my reason for stating that is that I was told it is true. That's easy enough. Okay. And what is it I'm trying to prove? I'm trying to prove that x is greater than 6. If I'm given this, so how do I go from here to here? Well, I've got some hints down here for us. I can use the addition property of inequality. Let's go ahead and use that. That says that as long as I add the same to both sides, remains true, right? So I'm going to add 5 to both sides. And then the other thing I'm going to use is the multiplication property of inequality, which tells me that if I multiply both of these by 1/2, it will remain true. That's the proof. I used given, addition property of inequality, multiplication property of inequality. Probably isn't wise to go beyond this without mentioning that if I were multiplying by a negative, I have to, if and then, right? Then, might as well put it in, I reverse the symbol. It didn't happen this time, but we don't want to forget that is the difference when we're talking about the multiplication property of an inequality. That's the difference from the multiplication property of an equation or an equality. Okay. If is the hypothesis, then is the conclusion. Remember this from geometry, don't you? The converse of a statement, you take your conclusion and you put that as your if, and you take your hypothesis and you put that as the then. So let's try it out. The first thing you should ask yourself is the conditional true? Is this true? If x is greater than 3. Let's draw a little number line. We can erase this in a minute. So I've got 0, I've got 3, I'm going to want to be looking at 4 as well. If x is less than 3, so less than 3, so that's what we start with, then x is less than 4. Yeah, that is true. So the conditional is true. I did my little diagram. We'll get it out of the way. We know it's true. All right. What about looking at the converse of this statement? Now we're going to take our conclusion and say if x is less than 4, so here's what we're saying, does it necessarily tell us that x is going to be less than 3? Well, no, because we could have x in here and it would be greater than 3. So this is the convert. This was true, and this is, if we can find any instance where it is not true, then we can call it false. I understand that there are places on this number line where this would be true, but as long as I can find one instance where it's false, I call it false. Let's try another. If 2x plus 1 is greater than 5, I guess we're going to have to work this one out too. Let me erase our previous work just so we always have an uncomplicated field of vision here. If Okay, let's simplify that. We'd have 2x is greater than 4, right? I'm going to subtract 1 from both sides, and that would mean x is greater than 2. Oh yeah, that is true. All right. So does it follow then that the converse is true? All right, if x is greater than 2, is it necessarily true that 2x plus 1 will be greater than 5? Well, it turns out that, and you can work it out yourself, but this is also true. So it could be that the converse is true, or it could be that the converse is false. You actually have to think it through. If each of the steps is reversible in a proof, then the first statement and the last statement are equivalent. So let's go back to the very first one we did. That we could reverse these steps without any problem. So this statement and this statement are equivalent. Going beyond, aren't I? The first statement and the last statement are equivalent. So I'm going to prove this. This is my given. And then I'm going to use the addition property of an inequality. And that's going to be my justification for what I do next. What I do next is 4x is less than 8. And then I'm going to use the multiplication property of inequality. And that will say x is less than 2. So this is equivalent to this. Which one do I like better? This one here, because it is simpler. Let's solve this by proving the statement and its converse. Oh my. Okay. We're saying if this is true, then this must be true. All right. So what am I going to start with? I'm going to start with the addition property of, I'm not going to write it all out, but you know, and that will be 6x, and I'm going to add a negative 7. Then I'm going to use the multiplication property, and I'm going to multiply both sides by 1/6. All right, so this was my given. This was my conclusion. They are equivalent to each other. This is equivalent to this. And can I reverse it? We said if each of the steps is reversible, then the first statement and the last statement are equivalent. So I'm going to go with the converse. So this is my given. And now I'm going to use, remember I'm doing everything in reverse. So this was the last thing I did. Now I'm going to do that to the given. And I'm going to multiply x and 5 by 6, so I'll get 6x is less than 30. Then I will use the addition property, and I'm going to add 7 to both sides, so 6x plus 7 less than 37. I was able to reverse it. If each of the steps is reversible, then the first statement and the last statement are equivalent. I've just demonstrated that. If each of the steps is reversible, then they're equivalent. But we haven't talked about what kind of step is not reversible. Well, if I have one where an expression becomes undefined, and I'll show you one in just a moment, or if I multiply by 0. So either one of these is a step which is not reversible, and I cannot be sure that I can take the converse, and the converse will be true. Okay, so what if we were to multiply both sides by x? Well, there is the chance that x might be 0. So could we be certain to produce an equivalent? No, we couldn't be certain. What if we were adding 1 over x squared? Now this is a situation where we might be going to something which is undefined, right? Because again, if x, this denominator, if it were equal to 0, that would create an undefined situation. How about adding 2x to both sides? Well, here, even if x is 0, adding 0 to both sides, that's going to be a equivalent equation or inequality. How about multiplying both sides by this? Now, in this case, even if x is 0, it's not going to affect this. If x were a negative number, it's going to become positive, so this one would be okay. It's not going to become undefined. Adding this to both sides, that would be okay. How about this one? Well, here again, we may get into a situation of it becoming undefined. What if x were negative 1? So this would be a no. Reasoning strategies. I'm just looking at the cartoon. He's only 50% bad luck because he's only half a black cat. Oh, I've had half a black cat before. Probably you have too. Some of you, a black and white cat. Solve problems using a test strategy. We often refer to this as guess and check. It's a low quality way of testing things. However, in the case of taking your PSAT or SAT or anything else where you want to quickly come up with an answer, and this might prove to be a very valuable kind of reasoning strategy. There's an example in your book. You can pause right now and take a look at it if you would like to. That's on page 98. A computer service costs 12 cents per minute for the first hour of use and 6 cents for each minute after that. This company received a bill from the computer service company for $59.10 for its first month of service. How much did it use the service? So we could try something we think makes sense. Well, 59.10. Its first month of service, and it only pays 12 cents a minute for the first hour. So 12 times 60 minutes in the first hour. So $7.20 for the first hour of use. That would leave all the rest of it at 6 cents a minute. So what would this be? 0, 9. So 51.90. I'll take 51.90 and I'll divide it by 0.06. Well, I'll do this. I'll just move this decimal place over here, and I'll say, okay, 6 goes into 51 8 times, doesn't it? 48. Bring down 3. Right 3. 6 goes into 39. Well, it goes 6 times. Make it a 30. Goes 5. Whoop. So that would be with no remainder. Isn't that nice? So that's how many minutes. And this was minutes. So I actually didn't guess and check here. It would take too long, I think. So 865, that would be at 6 cents a minute. That's the number of minutes. So these are the minutes. Plus 60 minutes at 12 cents a minute. And this gives us the total number of minutes. I think we better divide this by 60, don't you? Notice all I'm doing, I'm dividing by 6 and I'm moving this decimal point. And we'll figure out how many hours. Why would we talk about minutes when there's so many of them? We'll talk about hours. 6 goes in, so we're talking about 15 hours. And 25 minutes. So 15 hours and 25 minutes. And if I was supposed to be demonstrating guess and check, I guess I failed that because I didn't guess. I actually figured it out. But there may be occasions, even that one, where maybe for you, you could pretty well guess it right just looking at it. See you back in class. I'm looking forward to seeing you.